Okay, so before we begin, I would like to remind you of a couple of rules. We have the multiplication property of square roots and the division property of square roots. What pretty much that says, again, a times b under the radical is the same as a times b. And we can go both directions. It's an equal sign. So if I have two things under the same radical, again, same root, I can multiply them together and put them together under there. Division property, again, same thing. If I have a over b all underneath the square root sign, that's square root of a over square root of b. Again, likewise, you can put it together if it works out better that way. Alrighty. First example here, removing perfect square factors. So if I have the square root of 160, instead of just punching it into a calculator, giving an exact answer involves leaving part of it into a radical. So you'll notice here what we've done is I have square root of 160. That's technically the square root of 16 times 10, right? Didn't change anything. And according to our rules, I can break that up. Square root of 16 times the square root of 10. The reason I did that is the square root of 16 is a perfect square. So 4 times the square root of 10. Now, if there are more perfect squares than 10, you'd have to break that up further, but there's not. So technically, the exact answer is 4 square roots of 10. So for the got it, the square root of 72 is technically the square root of 36 times 2. And again, I picked 36 because 36 is a perfect square. So that's the square root of 36 times the square root of 2, or 6 times the square root of 2. Now taking a look here, same thing works with variables. I am able to pull out variables that are perfect squares. So taking a look at their example here, what is the simplified form of 54n to the 7th? So we've got to take a look here. What are the perfect squares? I'm just going to rewrite it in terms of some perfect squares, right? So we can say 54 is 9 times 6, and again I picked 9 because it's a perfect square. And n to the n to the 7th power, rather, can be seen as n to the 6th power times n to the 1st power. You can write the 1 there if you like. And again, looking for those perfect squares coming out. You got to think back all those rules we've learned, how to deal with powers and all that. And it's coming back to play here. So rewriting this, I'm going to have square root of 9 times square root of 6 times square root of n to the 6th times square root of n. Perfect squares here, 3 and n cubed, and everything else goes right back into the radical sign. So that's going to give us 6n on the inside. So 3n cubed times the square root of 6n. That is the simplified form of this. Now it looks crazier and worse than we started with, but it truly is if you go back and look at all of our rules. Alrighty, so on the example here then, we've got negative, or the opposite of m technically, times 80m to the 9th. So we're going to keep that opposite of m on the outside still. And then on the inside, we're going to be thinking about perfect squares. Well, 80, right, is the same as 16 times 5. Again, I picked 16 because, right, do you know why? Perfect square. And then m to the 9th is m to the 8th times m to the 1st power. That's an 8, I promise. Now we bring out those perfect squares. And again, once you start seeing this, you can just bring out the perfect squares, right? So this becomes the opposite of m times 4 times m to the 4th. And what's that leave inside? It's going to leave 5 and m. So 5m on the inside. On the outside here, we're going to have to go back and combine some like terms. So we're going to get, I'm going to bring that up here to the upper right. We're going to get negative m to the 5th power, right, times 4 times 5m. And again, not quite standard form there yet. Obviously, the coefficient has to go out in front. So 4, right, negative 4, because it's really like negative 1. Negative 4 m to the 5th power square root of 5m is the simplified form of this. I know it doesn't look more simple, but it truly is according to our rules and to standard conventions. Okay, so this part's a little more fun because we get the opportunity to multiply some stuff and then go back and simplify it all. So I'm going to take this and we're we're going to multiply it together. Again, reminder, square root of a times square root of b is the square root of ab. That means I can multiply all this stuff out. So here's what it really looks like. And I'm going to write it in different colors so you can see them here. 2, and then we have square root of 7t times 3, and then square root of 14t squared. So we're going to go back and multiply first, then come back through and simplify. So the 3 times the 2 just makes 6 out in front. That doesn't change. The inside, I'm going to have 7 times 14, which is 98. And then t1, t to the first power, t to the squared is t cubed. Now that looks nice, right? But now I have to go through and put it in simplest form. So I have to take a look on the inside. Perfect squares, right? So we're going to have 6 on the outside still. On the inside, we're going to have 49 times 2 times, and then t squared, that's my perfect square from the variables, times t. So the 49 is going to come out as 7, right? So I'm going to have 6 times 7 times t, because there's that t squared coming out. Inside, we're left with the 2 and the t. So 6 times 7 is 42. T, the inside, 2t. They're not allowed out. So think if something's not a perfect square, it's not allowed out. It's like keep it inside at a radical jail. I don't know, whatever you want to call it. But, so there you go. Simplified form. If that one was too much for you, go back, watch it again on that one. There's a lot of steps there. Alrighty, on this first one here, we're going to have 3 square roots of 6 times square root of 18. So that's, again, I'm not going to rewrite the problem here, but we're going to multiply this stuff under the radical. So that's going to be 6 times 18 is 3 square roots of 108, which is technically 3 times the square root of 36 times 3 on the inside. That's my perfect square I was looking for in there. That's a 3 right there, I promise. And so that's 3 times 6, the 6 coming out of radical jail, 3. So we end up with 18 square roots of 3. That's A, by the way. B, let's see here. So we're going to multiply everything underneath first, right? So put them all together in the same radical, because that's part of the rules. So we've got 2a times 9a cubed. So that becomes 18a to the 4th. Well, 18 is 9 times 2, and then a to the 4th is already a perfect square, so we're good there. So coming out of there, we have the 9 coming out as a 3, the a fourth coming out as a squared, and leaving the 2 underneath. And then C, I'm going to go ahead and multiply the outside terms first, right? 7 times 3 is 21. Multiply the inside stuff. So 5 times 20 is 100, and x1 times x5 is x to the 6th. Okay, so there we go. Let me rewrite this so it looks nicer. 21 square roots of 100 x to the 6th. Now the thing is, everything underneath is a perfect square. So this will come out, so 21 times square root of 100 is 10, times square root of x to the 6th is x to the 3rd. And completing that, 210 x to the 3rd is simplest form. And then finally, talking about the D there, in problem 3, can you simplify the given product by first, right, taking the one on the right and make it 14t squared, and can you simplify that first? Absolutely. We can pull that t out, and you can see the example down here. We can pull that t out of there first. So the t squared becomes just t on the outside, and then we have to leave the 14 on the inside, then go through and follow the other steps we've already had. So multiple ways to get there. Same answer, though, because of the same rules for how it should look in the end. Okay, so writing a radical expression. So guess what? Yes, we can make this into a story problem. My only question on this one is, okay, so this is one at the beginning of the chapter. A rectangular door in a museum is 3 times as tall as it is wide. what is the simplified expression for the maximum length of a ping that fits through the door? This one doesn't look like these guys could turn this on its other side and go through much more easily. I think so. But hey, we're going to go ahead and make it mathematically ridiculous. So the door is W units wide and it's 3 high. So W and 3W, right? And oddly enough here, we need Pythagorean's theorem. I know that's coming back to get you, right? So technically, this right here, right, makes a right triangle with 3W and W as the legs, and then Pythagorean's theorem for C, the maximum length of a ping that'll fit through it, even though you could just turn it on this other edge, in my opinion, but whatever. I don't know, we're not apparently thinking today. So, Pythagorean's theorem says that this D right here, or C, what are they're calling it D, I guess. We'll call it D as well. So D squared, that's the hypotenuse, is equal to W squared plus 3W squared. Don't forget to square the 3 on there. So D squared equals W squared plus 9W squared. D squared equals 10W squared. Now, in order to finish solving that, I have D squared. I don't care what D squared is. I know what D is. So D is the positive square root of 10W squared. Or D is the positive square root, actually it's W, right, times the square root of 10. That's what we're looking for here. So whatever these W's happen to be, now you can shove in real numbers, and get a much better idea of what we're actually talking about. So, okay, so for the got it on this one, it's almost the same problem, with the exception that this time the height is going to be 4 times the width. Still makes that lovely right triangle though there, and I'm going to call my hypotenuse C. So again, reminder, Pythagorean's theorem, a squared plus b squared equals c squared. So 4w squared, again we're going to square that 4, plus w squared equals c squared. So we end up with 16w squared plus w squared equals c squared. So that's 17w squared equals c squared. So c is then the square root of 17w squared. The w is only going to come out there as a perfect square because 17 is prime. So we're going to get w 17, so square root of 17 equals c. And that's a weird answer, but that's what it is. Okay, so on here, we're going to use those skills we practiced in the vocab for simplifying a radical expression. Remembering the rules, there are 3 of them there. Obviously, first of which we cannot put the there cannot be a radical in the denominator. I'm going to pop those rules up here just a second. And here they are. Simplest radical forms, a radical expression. Again, simplest form when each of the following has been met. No radicands have perfect squares other than 1. No radicands have fractions. No radicals in the denominator of a fraction. So we're going to slide those down here out of the way. So we take a look here. Obviously there's a fraction inside of the radical, so that's not going to work for us. And these two have perfect squares inside of them. So we can split it up. The division property, again, used sort of in reverse if you think about it that way. Square root of 64 over square root of 49. Square root of 64 is 8. Square root of 49 is 7. So 8/7 is the simplified form. In this top one, we've got 8x cubed over 50x. Again, all inside the radical, which is a big no-no. So first we're going to do is we're going to split them up. But actually before that even, reducing the fraction inside. They're both even, so I can reduce it to 4 over 25. And then x cubed over x reduces to x squared. Those are all rules we learned before, and I do expect that you know. Told you they were coming back to get you. Now we can split it up into 4x squared over 25, and again, square root of each. In the top, we can take out the perfect squares of 4 and x squared, making them 2x. The bottom square root of 25 is 5. That would be the simplified form there. So in here, this first one, remembering that we are supposed to break them up, so we have square root of 144 over square root of 9. Square root of 144 is 12. Square root of 9 is 3, which, by the way, is the number 4 in the end. There's A. For B, again, we're going to, before we break them up, I'm going to reduce. So we're going to say that 36, I'm going to write it all out for you, 36 over A and 4 over A cubed. Well, 36 over 4 is actually the number 9, right? So you think about division, so that becomes 9. And on the bottom, We're going to lose one here, and that's going to be gone, so it's going to become a squared. Again, all based on rules that we learned before. And so now we can break it up. Square root of 9 over square root of a squared. Square root of 9 is 3, and square root of a squared is just a, so 3 over a. And to finish it up here, this one's a little more fun. We have the square root of 25y cubed over z squared. And before we can do anything, there's nothing we can, before we do anything, there's nothing we can reduce. So you can go ahead and break them up. So we get 25y cubed under the radical on the top and the bottom, z squared. Well, square root of 25 is 5. Square root of, and again, we practiced this before, this is technically y squared times y, right? So one y comes out, the other y stays inside, and the bottom square root of z squared is z. And that is the reduced form of this radical, or simplified form. So we talked in the video and the vocab about rationalizing denominator. The idea is you can't have irrational numbers in the denominator, like square root of 7 is an irrational number. So to rationalize it by multiplying by a well-chosen 1. So what that looks like here is square root of 3 over square root of 7. We're going to multiply top and bottom by square root of 7 over square root of 7, because my goal is to get rid of the square root of 7 down here. So on the top that becomes the square root of 3 times 7, and on the bottom it becomes the square root of 7 times 7. So that's square root of 21 over square root of 49. And square root of 21 is square root of 21, no perfect squares I can pull out of there. And square root of 49 is 7. So there is the rationalized form of it. And when there's variables involved, we do something very similar. So we can take a look at the example up here. We're going to multiply top and bottom by, again, our goal is going to be to get rid of that bottom. Technically, they wrote it out as 2 square roots of 2n. And it's really a square root of 8 over n if you think about it, because we pull out the 4. So I'm again multiplying top and bottom by top and bottom down here because we rationalized it first. So you only have to multiply by the square root of 2n on top and bottom. Now you could have multiplied top and bottom by square root of 8 over n, square root of 8 over n. There's sort of some more reducing in the end. So again, pulling out this perfect square first, so we only have to multiply by the minimum amount of things inside of a radical, if you put it that way. So again, a well-chosen 1. So 2n times 7 is 14n, still under the radical. And 2n times 2n is 4n squared inside the radical there, 2 staying on the outside. And then when we go back and decide to simplify, that 14n stays on the top. There's no perfect square to come out. And on the bottom, obviously we can pull out the 2n and multiply it times the 2 and get 4n. Okay, so again, remembering we're going to use that well-chosen 1 here. So we'll start with the first one. Obviously, there is a radical in the denominator not allowed. So I'm going to multiply top and bottom here by a well-chosen 1. So square root of 2 over square root of 3. And I want to get rid of that square root in the denominator. So I'm going to multiply top and bottom by square root of 3 over square root of 3. And again, we know that's 1 because any number divided by itself, except for 0, is 1. On the top, that's going to give us the square root of 2 times 3. On the bottom, that's going to give us the square root of 3 times 3, which is 9. So on the top, square root of 6, square root of 9 is 3. Now here's the thing. Some of you are going to be tempted to go, oh, I can reduce that into square root of 2 over 1. No. This 6 is inside of a square root symbol, not allowed. You got to find some perfect squares to pull out first before you could reduce, and we can't do that in this case. So that is the rationalized form here. Taking a look at B, we have the square root of 5 over the square root of 18m. And so I'm going to say square root of 5, nothing comes out of there. And 18 is 9 times 2, so we have the square root of 9 times 2m. So on the top, square root of 5 over 3 square roots of 2m. Now that looks nice except for the fact that, again, I have a radical in the denominator, not allowed. So I'm going to multiply top and bottom by a well-chosen 1. In other words, the square root of 2m over the square root of 2m. And again, I say well chosen because, I mean, I didn't pick some random version of 1. I picked one that's going to help me get rid of this radical here. So on the top, we're going to have these two are going to be multiplied, so we're going to get square root of 10m. And on the bottom, again, these guys are multiplied, so I'm going to get 3 times the square root of 4m squared. Well, there's a perfect square coming out. I mean, that was by design. So we're going to end up with square root of 10m on the top. And on the bottom, we're going to have 3 times 2m, because they're coming out of the radical there. So square root of 10m all over 6m. And again, there's the rationalized form of that. And then C, again, before we do any work here, I'm going to break them up because I can't reduce anything inside first. So square root of 7s over the square root of 3. And my well-chosen one's pretty straightforward. I'm going to multiply top and bottom by the square root of 3 over the square root of 3. On the top, that's going to be the square root, so 3 times 7 is 21. The s stays inside with it. On the bottom, that's 3 times 3, which is square root of 9. So to finish that up, 21 does not have any perfect squares that I can factor out. So square root of 21s all over number 3. There you have it.